All right, so we're going to start lecture B by proving this first one. Okay, I've got it written on the board over there too. We'll look at it on the board. Proof of property 1. What are proofs? They are arguments, logical deduction. Starting with premises, things you're assuming are true, using things you know are true to try to reach some conclusion. Most people find proofs difficult because it's hard to see the connection. It's also difficult to see, typically, how to even start. We want to, again, prove this property here. I'll put the board here for the camera. This property here, that's the one we want to prove. Keep in mind that I'm assuming the typical things on little b. Little b must be positive and not equal to 1. That's in the background. I don't state that in the proof, but I could have and maybe even should have. Capital A and capital B must also be positive. Okay, so here's a proof. I guess I have the property on the screen. Start by assuming A and B are given to be positive numbers. That's a good way to start in this case. Suppose you got two positive numbers, capital A and capital B. When you're not sure what to do after that point, which is what happens to many people, you probably want to get some scratch paper out and just try writing things down that you know already are true. What would be an example of something you know already is true when you're thinking about logarithms? You know these two equations are true. So maybe you need to use one of them. Maybe, in fact, the first one is the true fundamental one. That's the defining feature of the logarithm. If you think of it as the power that b must be raised to get it. In this case, 1. So write that down. Write that kind of equation down based on the quantities that were given here, the capital A and the capital B. And maybe their product too, since we need to think about their product, A times B. That'll come later. By definition of logarithms, it follows that, or we can say that these two equations are true. I could have the words are true at the end, but you don't have to. By saying equality, you are implying that they are true. For this kind of proof, now how do you get past this point? For these properties of logarithms, you always end up using a corresponding property of exponents to prove it. And you're assuming the properties are true for exponents. That's actually a big assumption. That fact in and of itself is difficult to prove, and you might even say more difficult than what we're doing right now. But you got to start from some foundation, assuming properties of exponents are true. For example, like, let me use different letters. C to the x plus y is c to the x times c to the y. That's an example of one property of exponents that might be relevant. In fact, that is the relevant one. How could we use that? Well, we've got b raised to some exponents. I guess the b is kind of like the c. Maybe. So again, maybe on some scratch paper, try it. Try using that property with these two quantities. What happens? But this means by a property of exponents that we can say this equation is true. That equality right there is the property of exponents. The exact one I just wrote on the board. Little b is playing the role of the c. This is playing the role of x. This is playing the role of y. I mean, you could even call these things x and y initially if you want to, if that helps. But you don't have to. I could separate it out like this. Now, usually when you use this property, you kind of go the other direction. You add the exponents to get this. But you can certainly go the other back this way. You can separate those two things that are being added into the product of two things to those exponents. But wait a minute. By this line, I can make replacements. I can make substitutions. This equals capital A and this equals capital B. Exactly what I said right there. And here I'm just writing AB, which I didn't have to do. Dot means multiplication, but so does just putting the letters next to each other, right? Juxtaposition of two separate variables represents multiplication. Any ideas of what to do from here? Do you have any ideas? Are we done? Is that it? We're not quite done. Another difficult thing about proofs is knowing when we're done. Did we really prove what we wanted to prove? We're not quite done. How do we finish? I did mention we could go back to this defining property of logarithms, not only for inputs that are A and B individually, but even for their product, A times B, which we do need to think about. Look, it's in the equation we want to prove. I could have put that fact up in this line, but I'm writing it down here. Just for a little bit of variety, you might say. Well, on the other hand, by definition of logs, same reason as the first sentence, or second sentence I should say, b to the log base b of capital A times capital B is capital A times capital B as well. Not only does this equal AB, but this equals AB. We're almost done. What can we conclude from this? This equals capital A times B, capital B. This also equals capital A times capital B. These two things must equal each other. Can we cancel the little b's and be done? Effectively, you can, but you should really give a reason. You can, and that reason is the fact that log base b, oh, you know what, that's a typo. The fact that b to the x is a one-to-one function. I need to change this typo before I put it in the shared folder. Since b to the x is a one-to-one function, I wasn't careful enough there, we can conclude that the exponents are equal. Since b to the x is a one-to-one function, what does a one-to-one mean? It means if the outputs are equal, the inputs must have been equal. Here I'm plugging this quantity into b to the x. And I get this output. Here I'm plugging this quantity into b to the x, and I get the same output. The outputs are equal. Therefore, the inputs must be equal. The powers, this and this, must be equal as well. And that's enough to be finished, and we can say, praise the Lord. PPL. Actually, most mathematicians put QED instead of PPL. It's Latin for quod erat demonstrandum, and it means I demonstrated what I wanted to do, and I'm done. Okay, but we can praise the Lord too. Okay, so that would be, except for my mistake, a polished proof. Again, I'll fix the mistake before I put it in the Google Drive. You should practice this kind of pattern for the others. For these two properties. Practice it. You'll be able to use a note card for the exam, and you theoretically could put it on your note card, but you're going to need your note card for other things too, so it's better to just practice it and understand it. Work on understanding it too. You can visualize property 1, the same property we just proved. Say in the case where b is 2, so we're talking about log base 2. In that case, you could say this is true. Using different letters now, no capital A and capital B anymore, but little a and little x. Think of little a as a constant and little x as a variable. The black graph is the graph of log base 2 of x. Notice, for example, it goes to the point 2, 1, because 2 to the first power equals 2. It goes to the point 4, 2, because 2 squared equals 4. It goes to the point 8.3 because the third power is 8. As A increases from 1 to 2 here, notice there's both blue and red lines, though you only see a blue graph. Actually, I meant to make that graph kind of purplish. But that looks purple. I should have made that more purple. Red, blue, and purple, right? What is this illustrating? I'm doing both a horizontal compression and a vertical translation, and I get the same graph in the end when A is 2. This represents horizontal compression by a factor of 2 toward the vertical axis. This represents adding something to that. It's a vertical translation. Notice all the blue vertical lines are the same length, but the red horizontal lines are not the same length. The blue horizontal vertical lines are the same length because it's a vertical translation. The red lines are not the same length. It's not a horizontal translation, it's a horizontal compression. Everything's getting twice as close to the vertical axis here. The point 4.2 here goes to the point 2.2, right there. The point 8.3 goes to the point 4.3, right there. After the compression has been done. But you get the same graph either way. That's pretty cool. Oh, I forgot to do animation with this slide. Everything at once here. Here's some calculus-related properties of logarithms. They are continuous and smooth, at least on their domains, which is only when x is positive. When b is bigger than 1, which it usually is, we usually don't care about the case where b is between 0 and 1. The graph is increasing concave down. As long as b is bigger than 1, it doesn't matter what b is, the graph looks like this, increasing concave down. Y equals log base b of x when b is bigger than 1. One thing I forgot to mention is it also has a x-intercept at x equals 1. Log base b of 1 equals 0 since b to the 0 power equals 1. That's another fundamental fact of logarithms. So increasing and concave down. When b is between 0 and 1, the graph looks like a reflection of that graph across the horizontal axis. It still goes through 1 like that. We don't really care about this situation. Nobody typically really cares about it. I'm mentioning it here, and this is probably the last time I'm going to mention it. We will focus on this case, and we will focus almost exclusively after this class on the case where b is e, the natural log. Maybe once in a while b is 10, but we will almost always focus on the case where b is e. Somehow that's the best logarithm to use for some mysterious reason. We will actually figure out that mysterious reason in this class. Somehow e, base e, is the most special one to use. You can write these limit symbols. You can say the limit as x goes to infinity of log base b of x, in this case where b is greater than 1, is infinity, plus infinity. And the limit as x goes to 0, why do I put a plus sign? Is that a typo? Does anybody know why I have a plus sign there?
It's on the right side of 0.
Yeah, I'm letting x approach 0 from the right. I'm not saying 0 is positive. So 0 is very special. It's not positive and it's not negative. It's neither. I'm letting x go towards 0 from the right so that I stay in the domain of the log function. That's why. The function goes down forever and ever. It's got a vertical asymptote. And it never touches the vertical axis. It goes off to minus infinity. It goes down forever and ever as x approaches 0 from the right. In the case where b is between 0 and 1, you can say these facts as well, based on that other graph. This one, it's a little bit mysterious. The graph, again, is increasing and concave down. This fact being true means it does not have a horizontal asymptote. It's going to get above any horizontal line, no matter how high. Though it could take a really long time to do so. You'd have to go way to the right before you get above 1,000,000, for example. But it will eventually get above the horizontal line at y equals 1,000,000. It'll get above it at y equals a googol too. Okay, eventually. You have to go past the edge of the universe. That's how far you have to go. I'm serious. If you draw it in an ordinary scale, and imagine your drawing going out to the end of the universe, past the end of the universe, if you want this graph to get above y equals a googol, probably you have to go past the edge of the universe. That's my problem. I'm serious. Okay. Not proving that, but I'm guessing. Infinity is pretty big, right? That's the name of my blog. Infinity is really big. It is. It's really, really mind-boggling. Have you ever thought about living forever with God? Eternity? People have no idea how long eternity is. Yeah, they say, yeah, it's forever and ever. They have no conception of how to actually imagine forever and ever beyond just not dying. They have no conception of how long that actually is. A Google years? A Google to the Google power years? What? Okay, how's trigonometry? Wow, one subject right after the other. Why we want you to know your pre-calculus stuff well to be in this class. Even though we're reviewing it, we go fast. Here's the unit circle definition of cosine, sine, and tangent in a visual. What's going on in this visual? Focus on the upper left. That's the unit circle. Circle radius 1, centered at the origin. See this black dot going around the circle. As the black dot moves, it makes an angle. Given an angle, in radians typically, though you should be able to convert to degrees if necessary, what is the cosine of that angle and the sine of that angle? Let's draw a static picture, and then we'll think about the animation again. Pretend that's the unit circle. Radius 1 here, centered at the origin. Give me some angle. So we're talking about the unit circle definition, not a right triangle definition, though you should be able to use the right triangle definition. So katoa, right? If you need to. And you will need to on your assignment sometimes, including on the graded assignment, if you haven't gotten there. There's a situation where you need to figure out the area of a trapezoid, which is this trapezoid, in terms of a certain angle in the graded assignment. You're going to need a right triangle like this one here, or this one here. And you're going to need to use sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If necessary, one of those will be necessary. But mostly we want to think about the unit circle here. You got an angle theta, which, by the way, if this is the unit circle, and theta is in radians, radians is really natural because that makes the length of this arc also equal to theta. If this is the unit circle, and theta is measured in radian measure, this number is the same as this length. Why? Well, think about it for the whole circle. If this circle has radius 1, its circumference is 2 pi. And you should remember that a 360-degree angle is 2 pi radians. 180 degrees is pi radians. 90 degrees is pi over 2. 45 degrees is pi over 4. Should be flexible to go back and forth between those different measures. The cosine of theta is the first coordinate of this point, and the sine of theta is the second coordinate of that point. Which, if you draw a right triangle in, is the same as the lengths of these sides. Cos theta, sine theta. However, Once your angle gets bigger, like over here or way over here, then thinking about it with right triangles and lengths leads to errors, I should say. You really want to think of it in terms of the coordinates. Knowing that the cosine is the first coordinate and sine is the second coordinate tells you, for example, when you're over here, that the cosine is negative and the sine is positive, because the first coordinate is negative and the second coordinate is positive. And when you're down here, they're both negative. And when you're over here, first coordinate is positive, cosine is positive, but the second coordinate is negative, sine of that angle is negative. So you can quickly figure out the sign, positive or negative, of the cosine and sine functions. Do it, use it, okay? Use what I just said. You also know about special angles. And it is expected that, for example, you would know that cosine of pi over 6 is square root of 3 over 2. That's one of those memorized values. You know, pi over 6 is 30 degrees. You're right about there. Its first coordinate's pretty close to 1. This is just a little less than 1. 0.8 something. Sine of pi over 6, on the other hand, is not very big. I didn't draw this very accurately. It's bigger than I drew it. Sine of pi over 6, which is 30 degrees, is 1/2, 0.5. And you should be able to figure out from that, and based on this diagram, thinking about the sign, positive or negative, cosines and sines of other angles that are common, like 5 pi over 6. 7 pi over 4. 7 pi over 4. It's not quite 2 pi. It's going 7/8 of the way around. We'd be down here if the angle was 7 pi over 4. The cosine of that's going to be positive. The sine of it's going to be negative. And it's going to be a special number, 7 pi over 4. This would be square root of 2 over 2. And this one would be negative square root of 2 over 2. Or if you prefer, 1 over square root of 2 and negative 1 over square root of 2. You know, dividing by 0 is a mathematical sin. Dividing by a radical root is not a mathematical sin, even though your teacher might have made you think it was. Right? It's not a mathematical sin to write this. That can be an answer. But then your teacher said, no, can't leave it like that. Must rationalize the denominator. And write it like this. And you're like, okay, teacher, I'll do that, because you told me to. But in reality, you can leave it like that. It's no problem leaving it like that. So why do they make you do that? 2 reasons. One, it helps them check your work better, in not only that situation, but other situations, or helps TAs check better. 2 is it's a useful technique in other situations. It's not really so useful here. It's not a big deal. But there's other situations, including situations we'll probably talk about in the next 2 weeks, where this technique is useful, of rationalizing the denominator. There's even some situations where you want to rationalize the numerator, which feels really weird. So coming back here, we can quickly, from that definition of cosine and sine, draw their graphs as functions of theta. This one, this blue one, is the sine function. Notice it's measuring not the length of the blue line, but its displacement, so to speak. When it's above the axis, it's positive displacement, and when it's below the axis, it's negative displacement. It is an actual length when it's above the axis. But right now, that blue line is what I'm looking at there. That blue graph is measuring that displacement, the second coordinate. What about the cosine? What about this red graph? It is sideways. Yeah, I mean for you to look at this sideways. Lots of sideways in this class. That's the horizontal coordinate, horizontal component, first coordinate. The red line, that's going horizontal. It's positive when the red line is to the right of the vertical axis. The first coordinate of the black point is positive. It's negative when the red line is to the left of the y-axis. The first coordinate of the black point is negative, like right now. This is the sine graph. This is the cosine graph. In reality, you could continue theta, right? Theta could keep going around and around the circle, not just back and forth. These graphs can be continued in a periodic way. That's modeling oscillation. Kind of common kinds of oscillation. Same with this one. You can keep going forever and ever. You could be doing the rotation clockwise. You know, counterclockwise is the positive orientation for us. Clockwise is the negative. You could be going clockwise. You could let theta become negative and continue the graph for negative values of theta for both graphs. Very quick here, right? Quick description of cosine and sine to get to their graphs as soon as possible. The tangent graph is also there in pink. Tangent is the ratio of sine divided by cosine. I'm not going to explain that for the moment, but it is. It's got vertical asymptotes in the graph over there. General sinusoidal functions allow you to model any kinds of real pure oscillatory behavior that stays at a constant frequency and a constant amplitude. Heard those words in science classes before. Typically, for us, not necessarily in science classes, it's written in one of two ways. This way, I am using the sine function here, but I could use the cosine function. If I use the cosine function, I would still call it sinusoidal. By the way, the prefix co kind of means they go together. Sine and cosine go together, right? Just like cooperation, going together. You're working together. That's where co comes from. Not only in cosine, but also cotangent, for example, or cosine. F of t, and I'm using t as the independent variable because it is typically going to represent time in applications for us. Greek letter there, that's not a 0, that's a phi. Actually, this is interesting. Mathematicians tend to call this thing phi. Physicists tend to call it phi. I don't know what engineers and biologists call it. They probably go with the physicists and call it phi. I asked a Greek professor, is it phi or is it phi? And he said, no, it's phum. No, he said either one. Pho. It's either one, phi or phi, but I will tend to say phi. Or we might write it this way, which is a little easier to understand in terms of horizontal translations, but it's written the first way as well. There's a connection. Phi equals negative b times h. In other words, h equals negative phi over b. These letters have meaning. It turns out that the amplitude of this oscillation is the absolute value of A. What is an amplitude? Got one of these oscillations, these sinusoidal oscillations. It's got an average value that goes through the middle of the graph horizontally, sometimes called the midline. The amplitude is the vertical distance between that and the highest point. Also the vertical distance between the midline and the lowest point. Absolute value of the A is the amplitude. What's the B? The B is not the period or wavelength, but it's related to them. The peak-to-peak horizontal distance is called the period for us typically, because we're thinking about the horizontal axis being time. It's also called the wavelength sometimes, if the horizontal axis is distance. Wavelength. It equals 2 pi over b. B B itself is not the period or the wavelength or the frequency even, but it's related to all those things. I'm going to typically call the period capital T. So if capital T is 2 pi over B, that also means B is 2 pi over capital T. Right? Because you can multiply both sides of this equation by B and divide both sides by T. There's something called the frequency as well, often written with a cursive letter, but not always. Frequency is 1 over the period. If the period is in seconds, length of time in seconds, the frequency would be in 1 over seconds, which is called hertz. This is in hertz, Hz, if t is in seconds. This is 1 over seconds. Seconds to the negative 1 power, called hertz. Essentially the number of cycles per second is what it means. The C is the midline value. This may be shifted up from the typical graph or down. Here's your t-axis, here's your y-axis. And again, if the h is the horizontal shift, it's easier to think about this one first before you try to write it down. If you write it this way, and h is positive, it's a shift to the right. If h is negative, it's a shift to the left. Translations. And then you can write it this way by using this equation. Phi is negative b times h. Here's a summary of what I just said. The phi is often called the phase angle, even though it doesn't really seem like an angle, at least if you're only thinking about the graphs. That's why quotes are on the word angle. You're going to have some completion homework problems where you have to take some graphs and figure out what A, B, C, and H are. It's the easiest kind of problem when H is 0. The other thing you're going to have to do is figure out whether to use cosine or sine, and whether the A is positive or negative. Let me just verbally tell you, if the graph starts at its midline at t equals 0, then you should use a sine, not a cosine. And a positive A if it starts by going up. If it starts by going down instead of up, then use a negative value of A. Remember, it's the absolute value of A that's the amplitude. On the other hand, if the graph starts at its peak, the high point at t equals 0, then use a cosine with a positive A if it looks like this, and a negative A if it looks like that. The harder cases, and in those cases h is 0. The harder cases is when you have some horizontal shift and you got to figure out h as well. Okay? There's also a slide about inverse trig functions, but I don't have time for that. We are out of time. I will send you some links to Khan Academy or something else, or some other videos you can watch to try to help you if you get stuck.